So, in the interest of trying to stay on schedule somewhat, and because I'm really very nice and I don't want you to be bored today, I wanted to give you a short lecture on the material that we would cover in class. I expect you to watch this, and of course also you should have read the material in the book. We'll do some review type problems and questions in class on Monday to try to compensate for the fact that we weren't in class today. So on this snow day, let's dive into physics. So basically in chapter 23, we're going to start to make a connection between the forces that we've been studying and the fields that we've been studying and energy. So we're going to introduce the concept of electric potential. That will come at the end of today's little video. But we're also going to look at the connection between the electric field and the electric potential energy. That connection you should have seen in the pre-lecture video. We're going to learn how to calculate the electric potential energy of a collection of charges, how to calculate the electric potential that charges have, and also eventually look at equipotential surfaces and also the electric potential and how we can use it to calculate the electric field. Of course, those are all the goals for the entire chapter. We're not going to be doing all that today. Just one last plug. I will be assuming that you've watched the pre-lecture video for day 7. That's going to give you an introduction that's going to be more in-depth than what I'll do today on the link between electric fields and electric potential energy. So you really need to watch that. So just as a reminder from last semester, we talked about the concept of work. Work was expressed as the dot product of a force and a displacement. And in the cases where the force was not always constant or didn't have a constant orientation relative to the displacement, we could do that calculation in an integral of f dot ds. We found that this was related to potential energy, in that the work done by a force, sorry, I forgot the negative sign, the work done by a force was related to a decrease in the potential energy. Now, it's important to understand that in this relationship, the force and the potential energy are linked. That is, that the potential energy that we're talking about, which is going down or decreasing as the work is done, is the potential energy that is associated with this force that's doing the work. Examples that we did last semester. Oh, and there's some thunder snow, in case you heard that. We talked about the force of gravity and the potential energy due to gravity, which was mgh. We also talked about the elastic force of a spring and the potential energy due to the elastic force, which was 1/2 kx squared. So these were some examples that we did last semester. We're still looking at that relationship between work and change in potential energy. And in the pre-lecture video, we went through that derivation. But just to sort of review it very quickly, let's suppose that we place a charge right here, Q naught, in a uniform electric field. That charge is going to feel a force. The force is equal to Q times E. And so if we want to look at the work done by that force, it would be QE dot ds. Now, because of the dot product, only the displacement in the direction of the electric field is going to contribute to the work. And that's why when they're looking at these dotted lines for the possible paths of the particle as it moves from point A to point B, it doesn't really matter that it goes through the curvy path. What really matters is only really the distance that it moves in the y direction, because that is going to be the direction of displacement that is parallel to the force that's making it move. As it moves, if it moves with that force, we're going to see a decrease in the potential energy associated with the electric field. So basically what we're saying is that as the force moves the particle with the electric field, that force is of course doing work. That's what we're doing a calculation of right now. But as it does the work, the energy that was stored in the electric field that gave it potential energy is actually going to decrease. Makes total sense. We need energy to do the work. That's where the energy comes from. Now, just to review again some facts that we learned in the pre-lecture video. In the video, we looked at some different scenarios of charges moving in the electric field. Basically, to remind you, we looked at a positive charge that moved both with the electric field and against it, and the same thing was done with a negative charge. What things would happen as it moved with the electric field or against it. And so we want to sort of remember what what conclusions we had. Generally, the conclusions could be summed up as, if the charge moves with the electric force, which is given by Q times E, it experiences a decrease in the potential energy. So basically that is because the force associated with that electric field had to do work to make that movement take place. Therefore, we expect the potential energy or the stored energy to go down. However, when the cases where we had the charge move against the electric force, well, in order to make that happen, an external force would have to be present to make it happen. And that external force would be doing work on the system. And at the end, because of the charge was moving opposite to the electric force, or moving with the external force, which did work on the system, we actually would see an increase in the stored or potential energy. And so we should be able to understand both of those conclusions. I like to use the analogy of a ball rolling down a hill. So if I had a hill, and here's a ball right at the edge, we know that the ball will tend to roll down the hill because of the fact that gravity will act on it. So gravity will do work. Actually, it does positive work as the ball goes downhill. And this results in the gravitational potential energy that decreases as this happens. So the work done by gravity is positive, but the change in potential energy is negative. We should also remember that this is something that would happen spontaneously. We don't need an external force to make it happen. Of course, we do have to do something to make the ball start rolling if it's not right at the edge of the hill, but you know what I mean. Once it starts going, it just goes down naturally. Now, in the other case, what if we have the ball at the bottom of the hill? We have gravity acting on it. We need to apply a force in order to make it go up the hill. So the ball's not going to go up the hill naturally. We have to apply some sort of external or applied force in order to make it happen. The applied force will do positive work, but the force of gravity will do negative work. And as that happens, related to this, the change in potential energy will be greater. As the ball goes up the hill, the gravitational potential energy increases. This is related to the fact that an external force has done work on the system, which allows it to input a certain amount of potential energy or stored energy. So it's interesting to sort of, I think it's helpful to look at these analogies, because these are really analogies to charges moving along with the electric force or against the electric force. But a ball rolling down the hill is something that's a little bit more sort of easier for us to relate to, and that's why I like to use that analogy. Okay, so now we're going to try to figure out an expression for electric potential energy, and we're going to start off with the electric potential energy of 2-point charges, and we're going to derive an expression for that. The way that we're going to imagine it is I have a charge Q, which is going to create an electric field. And then we're going to put Q naught, we're going to allow it to move in this electric field. Now, the electric field created by charge Q, we can express as KQ over R. In order to give it a direction, we're going to make it radial, of course. It's a radial vector. And then we're going to look at the expression for work. Work is equal to Q naught, which is the charge that we're placing in the electric field, times the electric field, dotted with ds. And so this is going to be the work done on Q naught by the electric field created by charge Q. Keep in mind that this will be related to the decrease in the potential energy of that electric field. So let's do a little bit more with this integral. So we're going to substitute into the integral the expression for the electric field due to the charge Q. And we see that we have a dot product because of the fact that the electric field is a radial vector. The only displacement that will matter as the particle moves, see here, from point A to point B, the only displacement that matters is in the radial direction. Okay, so had a little accidental problem there. Hopefully we're back on board. So this is going to change to this integral, which will be K Q naught Q, and then the ds will turn into dr over r squared, because basically we're going to make this dr in the r hat direction as well. We're going to go from RA to RB. And so we have to do that integral. That one's pretty easy. It's just the integral of r to the minus 2 dr. And we get K Q naught Q minus 1 over r evaluated at RA and RB, which gives us K Q naught Q over RB with a negative sign in front of it. Then we would end up, when we substituted in the lower limit, but we subtracted it, I get two negatives, and I get K Q naught Q over RA. Keep in mind that this is equal to minus the change in the potential energy. So we had the work is equal to K Q naught Q over RB, negative, plus K Q naught Q over RA, which is equal to minus delta U, which is equal to minus UB minus UA, which is equal to minus UB plus UA. Doing a nice simple comparison between these terms, we can sort of write the general conclusion that U can be expressed as K Q naught Q over R. And so this is sort of the expression that we get for the potential energy of two point charges that are interacting, that are separated by a distance of r. Don't forget that K is equal to 1 over 4 pi epsilon naught, so sometimes we might see this written a little bit differently. So, like I said, we get this expression for the potential energy of two charges separated by a particular distance. And when we use this, remember, potential energy is a scalar, but it can have a positive or a negative value. It's all going to depend on what the sign of the two charges are. And so if the two charges are positive, the potential energy is positive. Likewise, if they're both negative. Remember, though, or realize that if the two charges have opposite signs, we're going to have a negative potential energy. One of the things that we might wonder about is where is U equal to 0? And basically, the answer is that the definition or the construct that we have is that U is equal to 0 when R is equal to infinity, which means if the two charges are infinitely far apart, their potential energy is equal to 0. The other thing we want to sort of go back and think about is, remember that we originally said that work is equal to the change in the potential energy. So one of the things that we use or think about in order to sort of make some sense about this expression, K Q naught Q over R, what does that really mean? It represents the work done on the test charge to bring it from infinitely far away from Q to its present separation. And when we say the work done, we should add the work done by an external force. And let's see why that's true. When we look at the potential energy of two positive charges or two negative charges, we should actually understand, of course, that these two charges, because they're alike, will be repelling each other. And so if we want to bring them from an infinite separation to the present separation, we're going to need an external force to do a positive amount of work, because it's going to have to push them together. And so one of the things then that we end up concluding is that when we have a positive potential energy, this actually can tell us something about how the two charges feel about each other. It is representative of the fact that they have a repulsive force on each other. And it would take an external force, a positive amount of work, to bring them together. At the same time, when we have charges of unlike sign, the potential energy is negative, and those two charges would attract each other. They actually would want to come together naturally. And so we would think of an external force actually would have to do negative work because they would naturally come together. Again, we would say that because the potential energy is negative, it tells us something about how the charges feel about each other, the fact that that is representative of an attractive force. Now, finally, we're going to look at one last thing for today's lecture. We're going to talk about something called electric potential. Electric potential is represented by the term V, and it's measured in volts. And so you might think that that sounds kind of familiar. So we start off kind of thinking about when we're talking about the electric potential energy, it was really an interaction of a charge with an electric field. In my derivation that I just did of the expression for electric potential energy, we said the electric field was set up by charge Q, and then we were placing charge Q naught in that electric field. But electric potential allows us to look at just the electric field, so we could get Q naught out of it. So electric potential we should think of is something that tells us something about the electric field itself. It really eliminates any other charges that are interacting with it. Through definition, and so this program doesn't use subscripts, V is expressed as potential energy over Q naught, or the potential energy per unit charge. So when we look at potential energy change, remember that would be equal to minus the work, just moving that negative sign that we had previously in this relationship, would be QE dot ds. This would represent the charge placed in the electric field the change in potential would be measured as the change in potential energy over Q, which would be equal to minus the work over Q, which could be expressed as minus E dot ds. Thinking about what we just said about V equal U over Q, we can have an expression for the potential of a point charge. It's just going to be 1 over 4 pi epsilon Q over R. Notice our Q naught is missing. And if you have a collection of point charges, you just simply add all the potentials together. They add up just as scalars would add up. So again, just to repeat what I had done, we found that potential energy, change in potential energy is equal to minus the work, which is equal to minus QE dot ds. Change in potential is change in potential energy over Q, which is going to be equal to minus E dot ds. And there's actually an interesting conclusion from this, because basically what this tells us is if we move a delta S in the direction of the electric field, then this relationship tells us that our delta V will be less than 0. We will move in the direction of decreasing potential. So when we look at the electric field due to a point charge, we would be able to say that as we move away from the charge, our potential is going to decrease. The opposite would be true is if we move towards the charge. Because of this relationship, the potential between potential and electric field, we actually introduce a new way of expressing the electric field. Before we had talked about it being expressed as newtons per coulomb, but now we can also express it as volts per meter. Those two units are exactly the same. They don't change the magnitude of the electric field at all. So we will talk a little bit more about this and sort of apply some of these concepts in class on Monday. But I hope that you enjoyed both your snow day and this video.